The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so far we've learned how to do double integrals in terms of x, y coordinates, or also how to switch to polar coordinates. But more generally, there's a lot of different changes of variables that you might want to do. Okay, so today we're going to see how to change variables. If you want, how to do substitutions in double integrals. Okay, so let me start with a simple example. Let's say that we want to find the area of an ellipse with semi-axes A and B. Okay, so that means, an ellipse is just like a squished circle. And so there's A and there's B. And the equation of that ellipse is x over A squared plus y over B squared equals 1. Well, that's the curve. And the inside region is where this is less than 1. Okay, so it's just like a circle, but where you have rescaled x and y differently. So let's say we want to find the area of that. I mean, maybe you know what the area is, but let's do it as double integral. So, or if you find that area is too easy, you can integrate any function over the ellipse if you prefer. But let's do it just with area. So we know that we want to integrate just the area element, let's say dx dy, over the region inside the ellipse, that's x over A squared plus y over B squared less than 1. Now, we can try to set this up in terms of x and y coordinates, set up the bounds by solving first for x as a function of y, if we do it this order, and, well, do the usual stuff. That doesn't look very pleasant, and it's certainly not the best way to do it. Okay, if this were a circle, we would switch to polar coordinates. Well, we can't quite do that yet. But an ellipse is just a squished circle. So maybe we want to actually first rescale x and y by A and B to reduce to the case of a circle. So to do that, what we'd like to do is set x over A to be u and y over B to be v. So we'll have two new variables, u and v. And we'll try to redo our integral in terms of u and v. So how do we do the substitution? So in terms of u and v, the condition, the region that we're integrating on, will become u squared plus v squared less than 1, which is arguably nicer than the ellipse. That's why we're doing it. But we need to know what to do with dx and dy. Well, here the answer is pretty easy because we just change x and y separately. We do two independent substitutions. Okay, so if we set, if we set u equals x over a, that means du is 1 over a dx. And here, dv is 1 over b dy. So it's very tempting to write, and here we can write, in this particular case, that du dv is 1 over ab dx dy. Okay? So let me rewrite that. Okay, so I get du dv equals 1 over ab dx dy, or equivalently, dx dy is ab times du dv. Okay, so in my double integral, I'm going to write AB du dv. Okay, so now my double integral becomes, well, the double integral of a constant in terms of u and v, so I can take the constant out. I will get ab times double integral over u squared plus v squared less than 1 of du dv. And that is an integral that we know how to do, well, because it's the area, it's just the area of a unit circle. So we can just say, oh, this is ab times the area of the unit disk, which we know to be pi. Or if somehow you had some function to integrate, then you could have switched to polar coordinates, setting u equals r cos theta, v equals r sine theta, and then doing it in polar coordinates. Okay, so here the substitution worked pretty easily. The question is, if we do a change of variables where the relation between x and y and u and v is more complicated, what can we do? Can we still do this, or do we have to be more careful? And actually, we have to be more careful. So that's what we're going to see next. But any question about this first? No? Okay. Okay, so see, the general problem when we try to do this is to figure out what is the scale factor, what's the relation between dx dy and du dv. So we need to find the scaling factor. So we need to find dx dy versus du dv. So let's do another example that's still pretty easy, but a little bit less easy. Okay, so let's say that for some reason we want to do the change of variables, u equals 3x minus 2y and v equals x plus y. Why would we want to do that? Well, that might be to simplify the integrand, because we're integrating a function that happens to be actually involving these guys rather than x and y. Or it might be to simplify the bounds, because maybe we're integrating over a region whose equation in xy coordinates is very hard to write down, but it becomes much easier in terms of u and v. And then the bounds will be much easier to set up with u and v. Anyway, so whatever the reason might be, but typically it would be to simplify the integrand of the bounds. Well, how do we convert dx dy to du dv? So we want to understand what's the relation between, let's call dA the area element in xy coordinates. So dA is dx dy, or maybe dy dx, depending on the order. And the area element in uv coordinates, let me call that dA prime, just to make it look different. So that would just be du dv or dv du, depending on which order I will want to set it up in. So to find this relation, it's probably best to draw a picture to see what happens. Let's consider a small piece of the xy plane with area delta A corresponding to just a box with sides delta y and delta x. Okay, and let's try to figure out what it will look like in terms of u and v. And then we'll say, well, when we integrate, we're really summing the value of a function over a lot of small boxes times their area. But the problem is that the area of a box in here is not the same as the area of a box in uv coordinates. There maybe it will look like, actually, if you see that these are linear changes of variables, you know that a rectangle will become a parallelogram after the change of variables. So the area of a parallelogram delta A prime, well, we have to figure out how they're related so that we can decide what conversion factor, what's the exchange rate between these two currencies for area. Okay. Any questions at this point? No? Still with me? Mostly? I see a lot of tired faces. Yes? Why is delta A prime a parallelogram? That's a very good question. Well, see, here, if I look at this side of the rectangle, say this vertical side, it means I'm going to increase y, keeping x the same. If I look at the formulas for u and v, they're linear formulas in terms of x and y. So if I just increase y, see that u is going to decrease at a rate of 2, v is going to increase at a rate of 1 at constant rates. And it doesn't matter whether I was looking at this side or at that side. So basically, straight lines become straight lines. And if they're parallel, they stay parallel. So if you just look at what the transformation from xy to uv does, it does this kind of thing. Actually, this transformation here you can express by a matrix. And remember, we've seen what matrices do to pictures. They just, take straight lines to straight lines. They keep the notion of being parallel, but of course they mess up lengths, angles, and all that. Okay, so let's see. So let's try to figure out what is the area of this guy. Well, in fact, what I've been saying about this transformation being linear and transforming all of the vertical lines in the same way, all the horizontal lines in the same way, tells me also I should have a constant scaling factor, right? Because how much I've scaled my rectangle doesn't depend on where my rectangle is. If I move my rectangle to somewhere else, I have a rectangle of the same size, same shape, it will become a parallelogram of the same size, same shape somewhere else. So in fact, I can just take the simplest rectangle I can think of and see how its area changes. And if you don't believe me, then try with any other rectangle. You will see it works exactly the same way. Okay? So I claim that the area scaling factor here, in this case, doesn't depend on the choice of a rectangle. And I should say that because we're actually doing a linear change of variables, so somehow the exchange rate between uv and xy is going to be the same everywhere. So let's try to see what happens to the simplest rectangle I can think of, namely just the unit square. And if you don't trust me, then while I'm doing this one, do it with a different rectangle, do the same calculation, and see that you will get the same conversion ratio. So let's say that I take the unit square so something that has size that goes from 0 to 1, both in x and y directions. Okay, and let's try to figure out what it looks like on the other side. So here, the area is 1. Let's try to draw it in terms of u and v coordinates. Okay? So here we have x equals 0, y equals 0. Well, that tells us u and v are going to be 0. Next, let's look at this corner. Well, in xy coordinates, this is 1, 0. If you plug x equals 1, y equals 0, you get u equals 3, v equals 1. So that goes somewhere here. And so this edge of the square will become this line here. Next, let's look at that point. So that point here was 0, 1. If I plug x equals 0, y equals 1, I will get negative 2 and 1. So this edge goes here. Then if you put x equals 1, y equals 1, you'll get u equals 1, v equals 2. So I want 1, 2. And these edges will go to these edges here. And you see it does look like a parallelogram. Okay? So now what's the area of this parallelogram? Well, we can get that by taking the determinant of these two vectors. So one of them is 3, 1, and the other one is -2, 1. That will be 3 plus 2, that's 5. Okay, this parallelogram is apparently 5 times the size of this square. Here it looks like it's less because I've somehow changed my scale. I mean, my unit length is smaller here than here. So, but it should be a lot bigger than that. Okay, and if you do the same calculations, not with 0 and 1, but with x and x plus delta x and so on, you will still find that the area has been multiplied by 5. So that tells us, actually, for any of a rectangle, area is also multiplied by 5. So that tells us that dA prime, the area element in UV coordinates, is worth 5 times more than the area element in XY coordinates. So that means du dv is worth 5 times dx dy. What's so funny? What? Oh. Okay, rectangle. Okay, is it okay now? Or did I misspell other words? No? Okay. It's really hard to see when you're that close up. It's much easier from a distance. Okay. So, yeah, so we've said our transformation multiplies areas by 5. And so du dv is 5 times dx dy. So if I'm integrating some function dx dy, then when I switch to UV coordinates, I will have to replace that by 1/5 du dv. Okay? And of course, I would also, here my function would probably involve x and y. I will replace them by u's and v's. And the bounds, well, the shape of my region in the xy coordinates, I will have to switch to some shape in the UV coordinates. And that's also something that might be easy or might be tricky depending on what region we're looking at. So usually we'll do changes of variables to actually simplify the region, so that it becomes easier to set up the bounds. So anyway, so this is kind of an illustration of a general case, and why is that? Well, here it looks very easy. We're just using linear formulas, and somehow the relation between dx dy and du dv is the same everywhere. If you take actually more complicated changes of variables, that's not true, because usually you will expect that there's some places where the rescaling is maybe enlarging things, and some other places where things are shrunk. So certainly the exchange rate between du dv and dx dy will fluctuate from point to point. It's the same as if you're trying to change dollars to euros. It depends on where you do it. You will get a better rate or a worse one. So we have to, of course, we'll get a formula where actually the scaling factor will depend on x and y or on u and v. But if you fix a point, then we have linear approximation. And linear approximation tells us, oh, we can do as if our function is just a linear function of x and y. So then we can do it the same way we did here. Okay, so let's try to think about that. So in the general case, well, that means we'll replace x and y by new coordinates u and v, and u and v will be some functions of x and y. So, well, we'll have an approximation formula which tells us that the change in u, if I change x or y a little bit, will be roughly u sub x times change in x plus u sub y times change in y. And the change in v will be roughly v sub x delta x plus v sub y delta y. Or the other way to say it, if you want in matrix form, is delta u delta v is approximately equal to u sub x, u sub y, v sub x, v sub y times delta x and delta y. Okay? So if we look at that, what it tells us, in fact, is that if we take a small rectangle in xy coordinates, so that means we have a certain point xy, and then we have a certain width. Oh, this is going to be too small. So I have my width delta x, I have my height delta y. This is going to correspond to a small UV parallelogram. And what the shape and the size of that parallelogram are depend on the partial derivatives of u and v. So in particular, they depend on at which point we are. But still, at a given point, it's a bit like that. And so if we do the same argument as before, what we'll see is that the scaling factor is actually the determinant of this transformation. So that's one thing that maybe we didn't emphasize enough when we did matrices at the beginning of the semester. But when you have a linear transformation between variables, the determinant of that transformation represents how it scales areas. Okay, so one way to think about it is just to try and see what happens. Take this side. This side in xy coordinates corresponds to delta x and 0. And now if you take the image of that, if you see what happens to delta u and delta v, that will be basically u sub x delta x and v sub x delta x. There's no delta y. For the other side, okay, so maybe I should do it actually. So if we move in the xy coordinates by delta x and 0, then delta u and delta v will be u sub x, so it will be approximately u sub x delta x and v sub x delta x. And on the other hand, if you move in the other direction along the other side of your rectangle, 0 and delta y, then the change in u and the change in v will correspond to, well, how does u change? That's u sub y delta y, and v changes by v sub y delta y. And so now if you take the determinant of these two vectors, okay, so these are the sides of your parallelogram up here. And if you take these sides to get the area of the parallelogram, you would need to take the determinant. And the determinant will be the determinant of this matrix times delta x times delta y. So the area in UV coordinates will be the determinant of the matrix times delta x delta y. And so what I'm trying to say is that when you have a general change of variables, du dv versus dx dy is given by the determinant of this matrix of partial derivatives. Okay, it doesn't matter in which order you write it. I mean, you can put, in rows or in columns. If you transpose a matrix, that doesn't change the determinant. It's just, any sensible matrix that you can write will have the correct determinant. Okay, so what we need to know is the following thing. So we define something called the Jacobian of a change of variables and use the letter J, or maybe a more useful notation is partial of uv over partial of xy. That's a very strange notation. I mean, that doesn't mean that we're actually taking the partial derivative of anything. Okay, it's just a notation to remind us that this has to do with a ratio between du dv and dx dy. And it's obtained using the partial derivatives of u and v with respect to x and y. So it's the determinant of a matrix u sub x, u sub y, v sub x, v sub y. The matrix that I had up there. Okay, and what we need to know is that du dv is equal to the absolute value of j dx dy. Or if you prefer to see it in the easier to remember version, it's absolute value of d of uv over partial xy dx dy. Okay, so this is just what you need to remember, and it says that the area in uv coordinates is worth, well, the ratio to the area in the xy coordinates is given by this Jacobian determinant. Except one small thing, it's given by actually the absolute value of this guy. Okay? So what's going on here? What's going on here is when we are saying the determinant of a transformation tells us how the area is multiplied, there's a small catch. Remember, determinants are equal to areas up to sign. Sometimes the determinant is negative because of reversing the orientation of things. But the area is still the same. Area is always positive. So the area elements are actually related by the absolute value of this guy. Okay, so if you find, minus 10 as your answer, then du dv is still 10 times dx dy. Okay, so yeah, I mean, I didn't put it all together because then you would have two sets of vertical bars. See, I mean, this is a vertical bar for absolute value. This is a vertical bar for determinant. They're not the same. That's the one thing to remember. Okay, any questions about this? No? Okay. So actually, let's do a first example of that. Let's check what we had for polar coordinates. Last time I told you, well, if we have dx dy, we should switch it to r dr d theta. And we had some argument for that by looking at the area of a small piece of, a small circular sector. But, let's check again using this new method. So in polar coordinates, I'm setting x equals r cosine theta, y equals r sine theta. So the Jacobian for this change of variables. So let's say I'm trying to find the partial derivatives of x, y with respect to r theta. Well, what is, okay, let me actually write them here again, just for you. And so what does that become? Partial x over partial r is just cosine theta. Partial x over partial theta is negative r sine theta. Sorry, I guess I'm going to run out of space here, so let me do it underneath. So we said x sub r is cosine theta. X sub theta is negative r sine theta. Y sub r is sine. Y sub theta is r cosine. And now if we compute this determinant, we'll get r cosine square theta plus r sine square theta. And that simplifies to r. So dx dy is, well, absolute value of r, dr d theta. But remember that r is always positive, so it's r dr d theta. Okay? So that's another way to justify how we did double integrals in polar coordinates. Okay, any questions on that? Where? Yeah, okay.
Are we switching from polar to xy or from xy to polar? Flip from what it is on the top one.
Yeah, so this one seems to be switching. Well, it depends what you do. See, so, okay. Actually, here's an important thing that I didn't quite say. So I said, you know, we're going to switch from xy to uv. We can also switch from uv to xy. And you know, this conversion ratio, the Jacobian, works both ways. Once you have found, you know, the ratio between du dv and dx dy, then it works one way or it works the other way. I mean, here, of course, we get the answer in terms of r. So this would let us, you know, switch from xy to r theta. But we could also switch from r theta to xy, just we'd write dr d theta equals 1 over r dx dy. And then we'd have, of course, to replace r by its formula in xy coordinates. Usually we don't do that. Usually we actually start with xy and switch to polar. But so in general, you know, when you have this formula relating du dv with dx dy, you can use it both ways, either to switch from du dv to dx dy or the other way around. And the thing that I'm not telling you, but now I should probably tell you, is, you know, I could define two Jacobians, because if I solve for xy in terms of uv instead of uv in terms of xy, then I can compute two different Jacobians. I can compute partial uv over partial xy, or I can compute partial xy over partial uv, if I have the formulas both ways. Well, the good news is these guys are the inverse of each other. So, you know, the two formulas that you might get are consistent. Okay, so useful remark. You know, so say that you can compute both these guys. Well, then actually their product will just be 1. So, you know, they're the inverse of each other. So it doesn't matter which one you compute. You can compute whichever one is the easiest to compute, no matter of which one of the two you need. And one way to see that is that, in fact, you know, we're looking at the determinants of these matrices that tell us the relation between the variables. So if one of them tells you how delta u, delta v relate to delta x, delta y, the other one does the opposite thing, it means they're the inverse matrices. And the determinant of the inverse matrix is the inverse of the determinant. So they're really interchangeable. I mean, you can just compute whichever one is easiest. So here, if you wanted dr d theta in terms of dx dy, it's easier to do this and then move the r over there than to first solve for r and theta as functions of x and y and then do the entire thing again. But you can do it if you want. I mean, it works. Oh yeah, the other useful remark. So I mentioned it, but let me emphasize again. So now the ratio between du dv and dx dy, it's not a constant anymore. Over there it used to be 5, but now it's become r or anything. I mean, in general it will be a function that depends on the variables. So it's not true that you can just say, oh, I'll put a constant times du dv. Yes?
With uv, you change from Cartesian coordinates to Cartesian coordinates. So when you change the polar coordinates, will be an approximation?
It would still work the same. You could imagine drawing a picture where r and theta are the Cartesian coordinates, and your picture would be completely messed up. It would be a very strange thing to do, to try to draw, I mean, I'm going to do it, but don't take notes on that. You could try to draw a picture like that, and then, a circle would start looking like, a disk would look like that. And it would be very counterintuitive, but you could do it, and that would be equivalent to what we did with the previous change of variables. So, in this case, certainly you would never draw a picture like that. But you could do it. Okay. Okay, so now let's do a complete example to see how things fit together, how we do everything. So let's say that we want to compute. So I have to warn you, it's going to be a very silly example. It's an example where it's much easier to compute things without the change of variables. But it's good practice in the sense that we're going to make it so complicated that if we can do this one, then we can do them all. So let's say that we want to compute this, and of course it's very easy to compute it directly. But let's say that for some evil reason, we want to do that by changing variables to u equals x and v equals xy. Okay, that's a very strange idea, but let's do it anyway. I mean, normally, you would only do this kind of substitution if either it simplifies a lot the function you're integrating, or it simplifies a lot the region on which you're integrating. And here, neither happens. So, but anyway, so the first thing we have to do here is figure out what we are going to be integrating. Okay, so to do that, first we should figure out what dx dy will become in terms of u and v. So that's what we've just seen using the Jacobian. Okay, so the first thing to do is find the area element. And for that we use the Jacobian. So, well, let's see. The one that we can do easily is partials of u and v with respect to x and y. I mean, the other one is not very hard because here you can solve easily, but the one that's given to you is partial of u and v with respect to x and y. So partial u, partial x is 1. Partial u, partial y is 0. Partial v, partial x is y. And partial v, partial y is x. Okay, so it's just x. So that means that du dv is x dx dy. Well, it would be absolute value of x, but x is positive in our region. So at least we don't have to worry about that. Okay. So now that we have that, we can try to look at the integrand in terms of u and v. Okay, so we were integrating x squared y dx dy. So let's switch it. Well, let's first switch the dx dy. That becomes 1 over x du dv. So that's actually xy du dv. And what is xy in terms of u and v? Well, here at least we have a little bit of luck. Xy is just v. So that's v du dv. So in fact, what we'll be computing is a double integral over some mysterious region of v du dv. Okay. Now, last but not least, we'll have to find what are the bounds for u and v in the new integral, so that we know how to evaluate this. In fact, well, we could do it du dv or dv du. We don't know yet. Oh, amazing. It went all the way down this time. Okay. So it could be dv du if that's easier. So let's try to find the bounds. In this case, that's the hardest part. Okay, so let me draw a picture in xy coordinates and try to understand things using that. Okay, so x and y go from 0 to 1. The region that we want to integrate over was just this square. Let's try to figure out how u and v vary in there. So let's say that we are going to do, let's say we're going to do it du dv. Okay, so what we want to understand is how u and v vary in here. What's going to happen? So the way we can think about it is we try to figure out how we are slicing our region. Okay, so here we are integrating first over u. That means we start by keeping u constant, no, by keeping v constant as u changes. Okay, so u changes as v is constant. What does it mean that I'm keeping v constant? Well, what is v? V is xy. So that means I keep xy equals constant. What does the curve xy equals constant look like? Well, it's just a hyperbola. Okay? Y equals constant over x. So if I look at the various values of v that I can take, for each value of v, if I fix a value of v, I will be moving on one of these red curves. Okay? And u, well, u is the same thing as x. So that means u will increase. Here maybe it will be 0.1, and it will increase to all the way to 1 here. Okay, so we're just traveling on each of these slices. Now, so the question we must answer here is, for a given value of v, what are the bounds for u? So I'm traveling on my curve v equals constant and trying to figure out, when do I enter my region? When do I leave it? Well, I enter it when I go through this side. So the question is, what's the value of u here? Well, we don't know that very easily until we look at these formulas. So u equals x, okay, but we don't know what x is at that point. Well, u equals x and v equals xy. What do we know here? Well, we don't know x, but we know y, certainly. Okay? So let's forget about trying to find u, and let's say for now we know y equals 1. Well, if we set y equals 1, that tells us that u and v are both equal to x. So in terms of u and v, the equation of this in uv coordinates is u equals v. Okay? I mean, the other way to do it is say that you know you want y equals 1. You want to know what is y in terms of u and v. Well, it's easy. Y is v over u. So let me actually add an extra step in case that's... So we know that y is v over u equals 1. So that means u equals v is my equation. Okay? So when I'm here, when I'm entering my region, the value of u at this point is just v. U equals v. That's the hard part. Now we need to figure out, so we start at u equals v, u increases, increases, increases. Where does it exit? It exits when we are here. What's the value of u here? 1. That one is easier, right? This side here, so this side here is x equals 1. That means u equals 1. So we stop at u equals 1. Now, we've done the inner integral. What about the outer? So we have to figure out what is the first and what is the last value of v that we'll want to consider. Well, if you look at all these hyperbolas, xy equals constant, what's the smallest value of xy that we'll ever want to look at in here? 0, okay? Let me actually, where's my yellow chalk? Is it? No. Ah. So this one here, that's actually v equals 0. So we'll start at v equals 0. And what's the last hyperbola we want to look at? Well, it's the one that's right there in the corner. It's this one here, and that's v equals 1. So v goes from 0 to 1. Okay? And now we can compute this. I mean, it's not particularly easier than that one, but it's not harder either. How else could we have gotten these bounds? Because that was quite evil. So I would like to recommend that you give it a try this way, in case it works well. Just try to picture what are the slices in terms of u and v, and how you travel on them, where you enter, where you leave, staying in the xy picture. If that somehow doesn't work well, another way is to draw the picture in the uv coordinates. Oops. Switch to a UV picture. So what do I mean by that? Well, we had here a picture in xy coordinates where we had our sides. And we're going to try to draw what it looks like in terms of u and v. So here we said this is x equals 1. That becomes u equals 1. So we'll draw u equals 1. This side we said is y equals 1, that becomes u equals v. That's what we've done over there. Okay, so u equals v. Now we have the two other sides to deal with. Well, let's look at this one first. So that was x equals 0. What happens when x equals 0? Well, both u and v are 0. So this side actually gets squished in the change of variables. It's a bit strange, but it's a bit the same thing as when you switch to polar coordinates at the origin. R is 0, but theta can be anything. Sometimes it's not always 1 point is 1 point. So anyway, this is the origin. And then the last side, y equals 0, and x varies, just becomes v equals 0. So somehow, in the change of variables, this square becomes this triangle. And now, if we want to integrate du dv, it means we are going to slice by v equals constant. So we're going to integrate over slices like this. And you see for each value of v, we go from u equals v to u equals 1. And v goes from 0 to 1. Okay, so you get the same bounds just by drawing a different picture. So it's up to you to decide whether you prefer to, think on this picture or draw that one instead. It depends on which problems you're doing.